So today we're going to talk about exploratory factor analysis, or EFA. We're going to look at extraction methods, rotation decisions, factor retention, and interpretation. And then we're going to walk through an SPSS example with screenshots. After this lecture video, you will be able to do an EFA with a difference data set for practice. The goal is for you to feel confident running and eventually teaching EFA. EFA is a method used to uncover the latent constructs that explain relationships among observed variables. We don't specify the structure in advance. Instead, EFA helps us figure out what that structure is. You'll see EFA in scale development, survey validation, psychological constructs, and education research. It helps reduce items into a smaller set of meaningful dimensions. So what are some of the assumptions and preparatory checks? First, let's talk about sample size. A rule of thumb is that anything over 200 in your sample is considered good, and anything over 500 is excellent. Large simulation studies have showed that factor recovery improves sharply after 200, so the more you have, the better. Some others say that at least 5 to 10 participants per item. So for example, if you have a 20-item scale, you would need to have 100 to 200. If your communalities are high, over 0.6, and loadings are strong, EFA is stable even with n equals 100. So if communalities are low, you would need around 3 to 500, which is best practice, this communalities approach. And there's a citation for you. Factorability. So the KMO, or the Kaiser-Meyer-Olkin test, measures the sampling adequacy, and we want to see a value of greater than 0.6. The Bartlett's test, we want to see it be significant. This measures if the correlation matrix is an identity matrix, meaning there are no significant correlations between the variables, and it's factorable. If you have extreme multicollinearity, you probably won't be able to do a factor analysis. So that's when you look at the correlations. If they're higher than 0.9, you won't likely get a significant Bartlett's test, and you most likely won't be able to do a factor analysis. There are different factor extraction methods. This is where SPSS defaults can mislead beginners. So when you pull up the factor extraction, and I'll show you that later in the video, PCA will be selected automatically, but that's not necessarily the best one we want. PCA is not EFA. It's descriptive, and it doesn't look at latent structures. Principal axis factoring is preferred for latent constructs, and that's what we'll use. And you can also look at maximum likelihood, which allows statistical tests of model fit. So what is a component and what is a factor? Components, which are from principal component analysis, are mathematical combinations of items that are created to reduce data. They use all the variance in the items, shared plus unique plus error, and they don't assume any underlying psychological meaning. They're simply statistical summaries. Constructs from EFA are latent variables that explain why items correlate. They use only the shared variance among the items, and they assume an underlying theoretical trait or dimension. They reflect something real we believe exists, something like motivation, anxiety, engagement, or whatever. So in short, components are statistical artifacts, constructs are theoretical latent traits. So looking at this, we can see that items 1, 2, and 3 load onto this particular component, where the arrows go from the variables to the component, meaning the component is a weighted combination of the observed items. Whereas factor, it goes from here to the items, and it incorporates error. The arrows go from the factors to the variables, meaning that the factor is the underlying cause of the shared variance among items. So this is a statistical remnant. This is a measure of some underlying factor. We have different options. Orthogonal is Varimax. These are factors that are assumed to be independent of each other. Oblique, these options are Promax or direct Obleman in SPSS. These factors are allowed to correlate. Oblique is usually preferred in social and behavioral sciences, and that's what we'll use in our example. Promax is faster, computationally simpler method that involves an initial orthogonal rotation like Varimax, followed by an oblique adjustment, while direct Obleman is an iterative process that directly calculates the oblique solution. We're going to use a direct Obleman. So then once you've done it, how many factors do you retain? Most people talk about the eigenvalues, and it's called the Kaiser criterion. When you look at eigenvalues that are over 1, it usually represents a factor, but this often overestimates. Another way of doing it is to identify the elbow in the scree plot. You look at the point of inflection and you look at the number of points before that inflection, and that's the number of factors that you will retain. Parallel analysis is most accurate when your data aren't very clear with eigenvalues or scree plots. And I'll show you how to do that, but SPSS, you have to use syntax in order to do that. But ultimately, theory should guide your final decision. So let's look at an example. We have a data set of 11 variables. We're trying to figure out how many latent constructs there are. So how do we do one? Here are the workflow for SPSS. Go to Analyze, come down to Dimension Reduction, and Factor. We'll take our variables and move them into the Variable box and click Descriptives. Then this initial solution will be checked. We're going to check coefficients, if not already checked, and KMO and Bartlett's test of sphericity. We'll click Continue and then go to Extraction. It will choose principal components for us, but we're going to scroll down and pick principal axis factoring. And then I couldn't fit it all on the slide, but you'll come over here and make sure you check scree plot. Then we'll click continue, and then we'll come back to rotation. We're going to select direct Obleman and leave it at that. Click continue. Then we'll skip scores. We'll go to options, and we want sorted by size. Click continue, and then OK. All right, now we can evaluate the correlations. You can see a big giant correlation matrix with variables 1 through 11 with variables 1 through 11. I've highlighted the ones of note. These are pretty strong correlations, and it's variable 1 with 2 and 1 with 3 and 2 with 3. Then we have 4 with 5, 5 with 6, and 4 with 6, and so forth. You can see that variables 10 and 11, we have some weird stuff going on here. We want to check our assumptions. We look at the KMO and Bartlett's test, and of course, this is test data, so everything behaves beautifully. We have 0.831 in the KMO, which is greater than 0.6, and it's almost approaching excellent. And our Bartlett's test is significant, which is what we want. So we can continue on. Then we look at communalities, which that's the abbreviation for communalities. H2, or communalities, is the proportion of an item's variance that is explained by the common factors. It represents variance in the items explained by the factors. Higher values indicate that items fit well with the factor structure. You can see all of these are fairly high. Total variance explained. So then we move to the next table, which shows how much overall variance the retained factors account for, helping determine how strong and meaningful the factor solution is. So right now you can see that we have 1, 2, 3 factors that are greater than 1. After between factor 3 and 4, we go from 2.3 down to 0.30. So it looks like these data represent 3 strong factors. You have the percent of the variance and the cumulative percent of the variance. When we get down to our third factor, we have explained 84% of the total variance. All right, let's look at the scree plot. So it displays the eigenvalues and helps identify the point where the curve levels off, indicating how many factors should be retained. In all honesty, they're never this clean. Now it looks like you go, oh, here's the elbow, it should be 4. But if you notice, the eigenvalue here cuts off between 3 and 4, so that's why we keep 1, 2, and 3. We only have really 3 factors. It breaks off here, and here's where the elbow is. So the factor matrix shows the unrotated factor loadings, but they're often hard to interpret and usually not used for final decisions, so we're just going to skip it. And then we go to the pattern matrix, which shows the unique contribution of each factor to each item after it's been rotated. This is the key table for interpreting oblique solutions. We want to keep the ones, the ones greater than 0.4 are considered meaningful. So you can see in factor 1, we've got 4, 5, and 6. In factor 2, we've got variables 1, 2, and 3. And then in factor 3, we've got 8, 9, and 7, or rather 7, 8, 9. And then we have 11, which is kind of hanging out there, and it's got some cross-loading. So cross-loadings, it's when an item loads on greater than 0.2 or more factors, and we want to consider dropping those. We also want to drop items with low communalities, which are less than 0.3, and we'll name our factors based on some conceptual meaning, which we'll get to in just a minute. The structure matrix shows the correlations between the items and the factors, including shared variance. Use it cautiously because it can inflate loadings, but we're not going to use it. We will just go to the pattern matrix. And then finally, you'll be given this factor correlation matrix. Correlations close to 0, the factor measures distinct independent construct. Moderate correlations, 0.2 to 0.5, they share some common variance but still represent separate dimensions. And then high correlations, factors may not be meaningfully different. Consider what to collapse. So we have low correlations, so close to 0. These ones here, right? These are them factored with them or correlated with themselves, so they're a full 1. We just ignore those. But these are close to 0, negative 1.128. And so we can say that each of these factors are distinct and independent construct. So what are our factors? Look at the items that load strongly on that factor. Focus on the items with loadings greater than 0.4. Ignore items with cross loadings. Read the items as if they were sentences and describe a theme. Ask, what do these items seem to have in common? Well, we have these, 4, 5, 6, 1, 2, 3, and 7, 8, 9. Okay, well, I don't know anything about this data set. All I gave you was a variable number 1, 2, 3, all the way down to 11. But what if I were to tell you that these were called engage, motive or motivation, and support, and then these two were mixed? Based on theory, I would say, okay, so these items that were loosely about engagement correlated together, and therefore I should keep those in one factor, which they showed numerically in one factor, and call it engagement. Same with motivation and same with support. This is where the statistics supports theory, but you don't just go in without any kind of idea of what your items are measuring. You intentionally create items to measure what you think you will be finding, and then when you do your exploratory factor analysis, the statistics will back it up or not, depending on how well you operationalized that particular concept. So back to parallel analysis. We use parallel analysis in exploratory factor analysis when we want to determine the number of factors to retain, especially when other methods like the Kaiser criterion, when we use the eigenvalue greater than 1 criterion, may be inaccurate. Parallel analysis is most important when the factor structure is unknown, when we don't know the number of factors, it's not obvious, when our items are messy, or if we have cross loadings, or if they're weak, if the scree plot is weird looking or ambiguous, or if we're building a new scale. When you're conducting a parallel analysis, you need to use SPSS syntax. Here in this slide, I'm showing you a link down below, which is from the text where he walks through an entire example. I will show you with the demo data that I've used in this PowerPoint from start to finish and include parallel analysis as well. Some things of note: you need to make sure that the relevant data set is open. You need to specify your variables. You need to run the program and evaluate. If the means are greater than the percentiles, you retain that factor. And then you go back and you would run the exploratory factor analysis and specify the number of factors you found in the parallel analysis, and I'll show you what that looks like. So this is syntax. When I say specify the variables from your data set, here you can see we have MR, FW, VP. These are from the video that I linked to before. We will go in and type in variable 1, variable 2, etc., all the way to variable 11. Here you can compute at the 50th percentile, or you can choose the 95th percentile. We will just choose the 95th percentile to check which factors to select. And then here you have to pick either 1 or 2. 1 is for PCA, which I've already said is principal components analysis. We're not going to use that. We're going to specify 2. Then you would go up to run, and then it'll show you this. Run, you click all, or you can just highlight and then use this little green arrow. But we're going to go run all and then evaluate the output. This is what it's going to look like. We've used principal axis factoring. We did 95th percentile. You can see it looks very similar, but here we have the raw data is greater than the percentile. This raw data is greater than the percentile. This one is greater than that one. And then here is where it's less than. 0.02 is less than 0.24. So we still see we have 3 factors. All these raw data are greater than the percentile, so we retain them. There are 3 factors. This isn't technically a scree plot, and it's better to evaluate these eigenvalues up here. But when the raw data, which is this light blue line, crosses the percentile and the means, that is when you cut it off. And it's kind of hard to see, but it's right before the 4, so we have 3 factors. And so why do we do that? Once you've run the parallel analysis, then you can rerun the EFA where you tell the computer how many factors to look for. So you go back to that principal axis factoring, make sure you check the scree plot, and here you would plug in, okay, we found 3 in our parallel analysis, so I'm going to tell it to extract exactly 3. And I will show you that in the example video. So some common pitfalls is when you use PCA instead of EFA. PCA is, like I said before, a data reduction method. EFA is a latent factor method. We want to do exploratory factor analysis when we're creating a survey. Overfactoring from eigenvalue greater than 1 rule, ignoring theoretical interpretability, and keeping items with cross-loadings. So here's an example of our APA reporting. An exploratory factor analysis was conducted on 11 items using principal axis factoring with direct Obermann rotation to identify the underlying latent structure. Prior to extraction, sampling adequacy was evaluated. The KMO measure verified the suitability of the data for factor analysis. It was at 0.831. And Bartlett's test of sphericity was significant at p less than 0.001. Indicating that the correlations among items were sufficient to proceed with factor extraction. Initial eigenvalues and visual inspection of the scree plot supported a 3-factor solution with a marked drop in eigenvalues after the 3rd factor. The first 3 factors had eigenvalues above 1.0 and collectively accounted for approximately 85% of the total variance. Based on these results, 3 factors were retained for further interpretation. After applying direct Obermann rotation, the pattern matrix revealed that items 1 through 3 loaded strongly on factor 1, all loadings greater than 0.6. Items 4 through 6 loaded on factor 2. Items 7 through 9 loaded on factor 3. Items 10 and 11 showed cross loadings across multiple factors and exhibited comparatively lower communalities between 0.3 and 0.35. Suggesting that they did not uniquely represent a single latent construct. Each factor was conceptually interpretable based on the content pattern of its loadings. Factor 1 appeared to represent engagement. Factor 2 reflected motivation, and Factor 3 corresponded to support. Items 10 and 11 were flagged as problematic due to their diffuse loading patterns and were considered for potential removal and follow-up analysis. Overall, the results supported a 3-factor structure representing 3 distinct latent constructs with 9 items loading cleanly and 2 items demonstrating weaker measurement properties. Okay, one final note. EFA is used when you do not yet know the underlying structure of your survey or construct. It shows how items naturally group together and helps you identify potential factors without imposing any prior assumptions. Confirmatory factor analysis, which is denoted CFA, is used when you already have a proposed factor structure and want to test how well the data fit that model. EFA discovers the structure, CFA confirms and evaluates it. CFA is not available in regular SPSS. You need to use something like SPSS AMIS, or using the Lavon package, Jamovi using the SEM package, or SAS or some other software package.